Okay, and based on the kinetics and the propagation mechanism, it can be divided in two classes for the polymerization. For the kinetics, for example, for step growth and chain, and then we can see here propagation mechanism can be polyadhesions, yeah, and polycondensation and so on. Okay, it is the polymer structure, as we know, is for example, it is within unit by n number, and this is, you know, this is the mass of phenyls. Yeah, we know this is the main chain or backbone, and this is the end group, and this is a side group or pendant group or functional group. And let me see here, we have for the example 3 type of the polymer. Yeah, we have here the polyethylene. Yeah, this is the ethylene mer, and this is vinyl chloride. Yeah, mers. So if you have the very long chains, it becomes the PVC, and the last one is polypropylene. This is the propylene mer. As you can see here, the change pendant or side of functional group will totally change the polymer properties, right? Okay. How about the type of polymer? We can divide it with several classifications based on its availability. In nature, we have the natural polymers. It means that the polymers provided by nature. Yeah. And then we have another one, synthetic polymers. It means that the polymers provided or made by the man. It can be automatically by machine or by handmade. We have also based on its backbone chains, for example, organic polymers. If the backbone chains consists of carbon or nitrogen, and also inorganic polymers, if the backbone contains outside of nitrogen and carbon. And also we have another based on its recyclability. We can divide the polymer become thermoplastics polymers or thermosetting polymers. And also based on its chain structure, it can be linear, branch, cross-link, and network. And also we have based on how its chain repeated. Yeah, we can have the homopolymer if the chain is same compositions. Yeah, for example, A, and so on. And also alternating polymers like AB, and random copolymer and block copolymer, and the last one is graph copolymer. I have a questions for you. What about the geopolymers? Okay, maybe we didn't answer it now. Okay, let's continue. We have also polymer family tree here. Based on the thermoplastic and thermoset or elastomer here, it can be, for thermoplastic cannot be reformed, will reform when melted, and for thermoset one is cannot reform by melting. It by need in the market, 90% it is not cross-link, it belongs to thermoplastic or thermoplastic polymer, yeah? And 10% about cross-link polymer, for example, epoxy, melamine, phenolic, and so on. Okay, this is the difference about thermoplastic and thermoset polymer. Yeah, for example, thermoplastic can be formed by the adhesions polymerizations, but the thermostatic one is oftenly formed by the condensation polymerizations. And about the structure in the chains, normally the thermoplastic is long chain linear polymer that held together by weak van der Waals forces. And for the polymer thermosetting plastics, it contains 3D network structure with a strong covalent bond. So the thermoplastic thermosetting plastic is very, very strong, and also it is cannot be melted, so it cannot be recycled. Okay, and the other difference usually become soften or heating and stiffen or cooling, but for thermosetting it does not become soft on heating. And about the price, yeah, normally thermoplastics a bit expensive compared to the thermoset plastic. So some application for mass applications, for example, a big structure like the body of ship, yeah, some structural materials, often used by thermosetting plastic or thermosetting polymer because of the cost considerations. And also thermoplastic is soluble in organic solvent, but thermosetting plastic are insoluble in organic solvent. Okay. Again, the other difference you can see here. Okay, for thermoplastic recycled polymer, we already know those symbols. Yeah, normally in the bottom of the package. For example, I pick up the water glass minerals here. We can see the bottom of this here, the code of this thermoplastic recycled polymer. For example, here for the glass plastic of our mineral water, normally is this used the PP, polypropylene number 5. So basically, it can be reused actually. Yeah. Okay. Here also we have the warning issue and application. Okay, I think I can share my PPT afterward after finish my presentations. Okay, you can student, you can read this my PPT. Okay, now we're going to discuss about the difference, yeah, between synthesis and manufacturing. Yeah. Okay, we have for the dictionary, the synthesis mean the combining of the constituent elements of spirit materials or abstract entities into a single or unified entity. It is the opposite of the analysis. Yeah. So the synthesis means combining, but the analysis a breakdown. Yeah. And synthesis can be a complex whole formed by combining, and also the forming of or building of a more complex substance or compound from elements or simpler compound. And but manufacturing mean the making of goods or wares by manual labor or by machinery, especially on a large scale. For example, the manufacture of television sets and so on. And also it can be the making or producing of anything. It can be, by definition, can be said as generations if the correlation to the biology term as the manufacture of the body cell. And we know if we draw the schematic diagram, the processing is in the outer line like this, and within the processing we have synthesis and manufacturing. In many cases, we have also we may also find the process in together with synthesis and manufacturing in one process. In next slide we can find this. Okay, the difference, basically the difference of the synthesis and manufacturing polymers, we can find this. For the raw materials, synthesis or the precursor can be liquid or gas because of the mass. The molecular weight is very low. Yeah. And in the manufacturing, the raw materials, it's already become the polymer or plastic in a condition of solid. Usually the form is pellets or scrap or small seeds. Yeah. And about the processing or reaction involved for synthesis, it can be involved with chemical reactions because of in the synthesis we make a polymer from mass. It can be the polymerization process. But in the manufacturing, it can be physical or mechanical processing like crushing, milling, melting, and forming or casting, or simultaneous with synthesis. And about the final product form, synthesis become a polymer. It can be in raw form, like solid parts, for example, pellet, rods, bars, etc., or in the final form of the polymer. But the manufacturing process, yeah, it's the final product formed to become a product for specific applications like petals, sheet, and electronic component, cookware, etc. Or simply said, synthesis is an initial step of a polymer processing, and manufacturing is a further step of polymer processing to produce or result of final products. Okay, so we can distinguish the difference between the synthesis and manufacturing of polymers. I have another questions for you, for students. How many polymers can be made? How many polymers can be made? Maybe we can say this many polymer, yeah, almost unlimited, because we can modify the polymer with another substance. Yeah. So basically, we have many elements, in this periodic table. We can modify, yeah, polymer in even in not pure condition. I mean, in a composite maybe. But for polymer, also you can make it, yeah, in the very many type of the polymer by combine it, blend it, and so on. Okay, in extremely words, yeah, we can say there is no life without polymers. Yeah, as we can see to the conditions with coronavirus, they are consist of the very basic protein structure, yeah, such as amino acid, for example. So it's also said as the polymers, yeah, because of the small part of living body is cells, yeah, can be said as polymer. Well, this is our main topic, the polymer processing instrument. We're gonna discuss about this instrument used to synthesis and or manufacture of polymers. Yeah. Before we go there, we have information about the plastics new for the global market for plastic product. It is the information for last 3 years. The compositions of the plastics have already applied, already used in our daily life, is on the business research company. 39% it is other plastics. I mean, it means that many plastic combined and modified, yeah, and 19% it is from plastic packaging materials, yeah, and 60% for piping, yeah, and also 11% about plate, yeah, sheet, except packaging and chip manufacturing, and 5% about the polystyrene foam, and 6% urethanes, and 7% plastic bottle manufacturing. So our bottle plastic is 10%. But as we know, after I forgot 2015, some researchers published about the the oceans pollutants of the plastics after China. Indonesia is the biggest one. Yeah. So the world provide some rule more tight to make regulations about the after-use plastics, yeah, and also Indonesia. So we have to reduce the plastic uses in our daily life, because of there are many pollutants can be produced by the plastics. Even in microplastics, as we know, it can be polluted, can be dangerous for our life. Okay, then it is a schematic of polymer processing flow diagram from the raw materials of the polymers, can be pellets, scrap, flakes, and so on, or it can be the monomer that in the process to make a product, yeah, involving the polymerizations within the process. So we have the polymer products here. So we have the line of processing for the raw material as the polymer, it's processing here, and the monomer, the processing including in situ polymerizations. And to producing the polymer product, it have to find or comply with technical standard. For example, you know, the standard for example for food grade materials, for NSF standard from America, and our country has also for SNI standard national Indonesia. Some code of process should be met with the specific standard, yeah, in order to be safe for food. And also the properties of the materials, not only for the products, but also the raw materials have to comply with the specific properties to get the polymer product with good classifications or best product quality. Okay, for the polymer or plastic processing, we can divide it in two classifications, two big classifications. Malting base, it means that the process or the process should use the malting for the to form the final product of the polymer. And the other one is the imaging base of the polymer or plastic processing. Okay. For the imaging phase, it can be said as non-molting, slicing, or layering phase, and also it can be said also as rapid prototyping, processing, and also additive manufacturing. We can commonly say as 3D printing of the polymer processing materials. What are the difference of those two kind of the classification of polymer processing? Let's see the novelty method. I think the molding base, it is kind of conventional method, and the imaging base can be modern, and it is a novel method, yeah. And based on the minimum number productions for the molding base, yeah, it needs minimum order, yeah, or mass productions. But for the imaging base, we can make it a unity or only one piece. It means the minimum order production is no minimum order. Let's see about the precision unit product. Yeah, the molding base, the precision is about middle to low, but for imaging base, it's a high precision of the product. And initial invested cost, I think molding base is very high because the infrastructure to make mass production is also high. But for the imaging base, it is typically low, but it is also depend on the type of 3D printer. Yeah, but commonly it is typically lower than the molding base polymer processing investment. Okay, this is the most important process parameters consideration that we have to looking at when we process the polymers from the raw material to produce the final product of the polymers. First is melting point, and then secondly viscosity, and we can say this in the term of mechanical engineering, track flow, and also modulus elasticity or plasticity, and curing or solidification time. All these parameter processes related to the viscoelasticity and rheology. that in this last part of this slides, I will give you an example related to this. Okay, this is dependency of viscosity to molecular weight. We have the equation of this, yeah. Alpha is this constant, and also K constants. That alpha below the critical molecular weight, alpha become equal to 1, but above the critical molecular weights, alpha become 3.4. Yeah. And dependency of viscosity to temperature, we have this, we'll have WLF equations like this. We have the reference temperature like TS here equal to C1 become to 8.86 and C2 101.6. But for TS, similar or equal to glass transition temperature, C1 becomes 17.44 and C2 51.6. And zero viscosity mean, it is determined by rheology measurement by dynamic viscosity at zero frequency. Okay. Yeah, we have some example of polymers or plastic processing. Yeah, that actually there are many process from traditional to modern one, but in major process of the polymer or plastics, those 7 process majority used in home scale, also in big industrial scale. Yeah. It is including extrusions, injection molding, blow molding, thermoforming, pressure forming, rotomolding, and 3D printing that we will discuss one by one in the next slide. Okay, for the extrusions, yeah. Commonly the extrusion process, the screw extruder using single, it can be also using twin or double screw extruder. What the difference? Yeah, this is the table of differences of the this single and or twin screw extruder. Yeah, for example, for single screw extruder, yeah, there are no fans. Yeah, but for the twins, actually there are fans present. Yeah. And then you know, for mixing efficiency, the twin screw extruder is excellent. Yeah, good, more than mixing efficiency of single screw extruder. It is pure mixing efficiency. What about the cost? Yeah, of course, because yeah, twice, yeah, because twin screw extruder is twice the price. Of course, the cost more than single screw extruder. The power, of course, yeah, as the sequence of the consequence of the process. Twin screw extruder more higher than the power consumption of single screw extruder. Okay, let's see next slide. Yeah, the extrusion machine forms the basis of nearly all other polymer processes. Yeah, because this is very common machine that's used in many industry. That basically involves melting polymer pellets and extruding them out through a two-dimensional die. Yeah, two-dimensional die. This is some type of the products can be resulted from the process of the extrusion process. This is schematic diagram of the machine of the extrusion process of the polymer or plastics. Here the left side is a gear block to maintain the movement of the machines, especially to control the movement of the screw here. Yeah, this is the motor. Okay, this is a feeder barrel. The color one is this the heater. It's mean I give the different color to give schematic heat is from left to right. The heating is higher. The right side is more heat. Okay, this part is nozzle and this is die. Okay, this is the profile of pressors as the function of the barrel length to reduce ratio. Initially, in the area P1, it is the feeder area. Yeah, you know, the pressures rise up like this and then increase again after entering the compression area P2 and P3, and finally the maximum pressures rise at the P4 here in the last part of heater in the barrel, and in the area of nozzle the heater the pressure slow down, and finally touch with the air. It means the pressure is in the normal condition of pressures. Okay, and this is the melt flow in the single screw extrusion. I think it is the reverse way. Yeah, it is a that way, but it is a that way. Okay. Okay, let's see short movie about the extrusion process. Three minutes, yeah. Excuse me, can you hear the sound of the movie? Steven?
Not, cannot, Dr. Sigit.
Okay. How to share the sound?
You can share by presenting the tab. A tab. There are three choices, right? Your entire screen, a window, a tab. If for video you use a tab.
So should I stop sharing first?
Yeah, and then you share the video by choosing a tab.
Oh, okay. Share tab.
There are three choices. Yes, a tab.
Oh, okay.
And then you play the video. Have you clicked the
Wait.
Okay. So many. Can you try it again?
Sorry, I usually use the Zoom. I'm not used to this one.
Google Meet.
Okay, wait.
Present now. Okay. Just play the video.
Is it? No sound?
No sound. Oh, the video is in the slide, right?
Slide. Yeah.
Oh, that's why I think it cannot be heard by us.
Okay. Just see this. Okay.
Yeah. Maybe you can explain during the process.
Oh, okay. Well. Okay. Oh yeah. So this is the raw materials. You know, this is the seed of the polymer raw material. Yeah, this is the attract by vacuum into the feeder area here, and then some adjustment. If we need to add some coloring. Yeah. So the sheet or the raw material added with the color agent, and then yeah, this is the screw. Yeah. As we can see here, even we here we have triple screw. Yeah. Yeah. After some adjustment by electronically by control, is, yeah, you know, this is the result of the extrusion process. This is the melted polymer drew out from the extruder. This is the result. Yeah, basically the principle like this. Yeah, for the next step, to make final products, for example, in this case, maybe about the you know, the product of the filament, yeah, like rod or stick. Yeah, after the extruder come out from the extruder machine, yeah, it cooled by water here. Yeah, to solidify, fast solidify, yeah, here, to make a continuous product like wire or filament. This is like the conveyor to control, yeah, control the size, distribution of size. Yeah. Okay, the final product calibrated for the size. Yeah, to see how homogeneous the size of the product. And then the last one is winding up to store the product in the specific packaging. Okay, let's see the next slide. Okay, the next one is injection molding. Yeah, the previous one is extrusion. This is injection molding. So this is the machine. We have the part of here injection molding, and this is injection part. It is the molding part. Yeah. Principally, we have several steps from the raw material to become product of the solid polymer, through this injection molding. The first one is make liquid polymer from the screw extruder here. So the mold closes and screw begins moving towards the injection part here. So the polymer come into the mold. Yeah. Then the cavity, yeah, the molding within in the molding fills as the screw moves towards as the plunger. And then the cavity is packed as the screw continues to move toward as part solidifies, to ensure that the liquid polymer filled up all the hole in the mold. Yeah. So no hole, yeah, remain in the molding. The next step is the cavity cools as the gate freezes. Yeah, the gate freezes off and the screw begins to retract to plasticized material. Yeah, for the remain time to release to let the material solidified. Yeah, and then the mold open for part ejection. Finally, to cycle process to go to the first process again. Then we have the final product of the molded plastic product, or polymer product here. some injection molding parts of the polymers like this, some piping, connector like this, and some the end of the parts of the tube. Yeah. Okay. And let's see the process. Yeah, this is injection molding. Yeah.
Yes.
Yeah, this is the room of molding that usually, yeah, make the polymer molded inside this. Yeah. Yeah, this is the molding. Yeah. Okay. This is the molding. Yeah. After the polymer melt enter to the molding from the extrusion part, enter to this molding, then yeah, the molding will be automatically tied, yeah, to make the polymer formed as the form of the molding. Yeah, so here we can, as we can see, there are many molds used. Yeah, yeah. This is a bucket. Yeah, this is the mold. Yeah. So the type of the form or the form of the polymer products, it depends on how the mold designed. Yeah. So we have two parts. The negative part, yeah, like this. For example, we would like to make like a bucket. This is negative part, yeah. And we have the positive part, like this, the positive mold, yeah. Okay. So the polymer fill the area or hole in between the positive and negative mold. So here, yeah. Okay. After several times, some second, the solidified of the polymer in the mold, and then the mold released, and finally we have the product. Okay, we speed up this. Okay, and this one is the injection blow molding. Yeah, we have injection molding without blow in the previous one, and now we are going to see the injection with blow molding. Okay, let's see. Yeah, like this. This is dies. Sorry, this is dies head. Yeah. That the polymer melt come out from that, and you know that this is moved to form the polymer melt soft polymer. Yeah, and you know this is the plunger that's inserted within the polymer is the like a gas, yeah, and blow it to deform the polymer, so the soft polymer fill up all the molds, yeah, fill up all the hole of the mold, as that's the design of the product. Okay, after solidified completed, the mold released, and finally we get the final product like this. Yeah, for example, this is like a container or plastic barrel. Yeah, the very basic difference of the injection molding with injection blow molding is the the existence of blowing. Yeah, blowing. So the final product of the polymer formed with the blowing process. There is like the big design. Okay, let's continue the next one. Yeah, this is the principle of injection blow molding. Yeah. This is the material. Yeah, soft polymer. We say this as cup and enter into the mold. Yeah, the mold. This I see this is negative mold. Yeah, we can see it's Parisian mold. Yeah, and then we have the negative mold like this to press the liquid polymer or soft polymer, so the polymer can and added with blow air inside to fill to form as the form of the mold like this, and finally release the mold, and we have the final product. This is the injection blow molding. This is the product and some product. Okay, and we also have the extrusion blow molding. Yeah, generally this process used to make bags, or films and sheet of plastics or polymer. So injection polymer enter the mold and blow with the air, and then air released, and we get the plastic sheet or plastic bag like this. This is the process of the injection of the polymer to make a plastic sheet. This is 2 minutes 56. Let's speed up this. This is the concept. Concept of all the process, and then this is the pellets or polymer sheet. As usually, this is the color agent if we need to add the color to our product. Inserting the polymer sheet into the this is the plastic with the blowing. There are some specific pressure to use to ensure that the plastic resulted with the homogeneous thickness. You see here, like a balloon. On the top, the plastic will wrap, so the forms become sheet like this. Okay. And finally, the packaging like this after the quality control. Okay, let's see the next slide. The next process is the thermoforming. It is also the common process of the polymer processing to make some product. So we have the mold. The form of the mold is similar with the final product resulted. The process can be seen like this. You can see this is Yeah. I think speed up this one. Yeah, this is the mold designed. You see, this is the mold and this is the product. And this is the product. So these plastics or polymers will be formed by using pressing it into the mold. So it can be formed, like the mold, the final product, like this. Okay, I can speed up this. Yeah, thermoforming. This is thermoforming. Okay, and the other one is rotomolding. Yeah, rotomolding means that the polymer processing using the rotations process, while the polymer sheet or polymer raw materials inserted to the mold, and then the molding rotated while heated. Yeah, so the form of the product is similar with the mold. Yeah, let's see the process. This is the concept of the rotational molding. This is the border of the polymer, and heated up and rotated, and after it cooled, and we got the solid polymer, and we have the form like the mold, like this, and finally it can be released, become the polymer product. Yeah. Okay, let's see the process of the rotomolding. Yeah, see, this is the polymer raw material after inserted. Yeah, you can see here several type of mold. Yeah, this is chamber of square chamber like this, and this is cylindric chamber. Yeah, you know, he's the heated. Yeah, it is like the conventional process. Yeah, the polymer raw material inserted to the mold. Yeah, then the molding rotated and together with the heated up, so the polymer inside the mold become liquid and and form similar with the form of the mold. After cooled, we can have the final product of the polymers or plastic. Yeah, like this. Yeah. Okay, this is the rotomolding process. Okay, this is the last one process. It's the most modern process of polymer processing by 3D printing. I have the question for you, student. Can you see what is the difference between left side and right side image? Maybe some student can comment.
Please comment. What is the difference between the left and right, student?
Yeah, from the raw material, you in the right side, we can see some liquid here, but the left side no liquid. Maybe any student can answer?
Nur Fatihah said that rigid shape. Answer that this is a rigid shape. Which side is a rigid shape? Nur Fatihah from the chat room.
Oh, wait.
Okay,
Sorry.
anyone can answer the question? What is the difference between the left side and the right side?
Okay. Okay, maybe I give the answer.
They all
Yeah.
shy.
Yeah, let's see what the difference in between this process, because this kind of 3D printing process is very well known today. Yeah. Okay, this is melting base and this is light base processing of 3D printing. Which one the light? Yeah, can be projected from the top, can be projected from the bottom. Yeah, from the bottom. Okay, let's see. Yeah, another difference. Yeah, for the raw material, this is the using the solid polymer. We set this filament. So the filament inserted to the this part, and we have nozzle here. Yeah, nozzle here, but here's without nozzle, because of the raw material is liquid. We said liquid pre-polymers. It's mean that the liquid is not polymerized yet. Yeah, so the polymerization is initiated by lights. Yeah, by lights. That the lights projected uh, um, with the specific form, like the layer by layer. Yeah, layer by layer. Okay. And for the patterning tools, yeah, this is use the nozzle, yeah, heat assisted nozzle. So the nozzle should be heated up. So the polymer feeder here, polymer melted and formed by patterning by computer control. Yeah, but here using the projected light. Okay, and the solidification process, and the left side, it is using the standard temperature and pressure polymerizations. So it's in the normal conditions. Yeah, solidification process, but this is used the photo or light assisted polymerization, because without light the pre-polymers is stay in liquid, cannot form the solid like this. Yeah, okay. Then the prototyping process. Yeah, this in the left side, yeah, melting base, the nozzle or bed can move x, y, z directions. Normally, the bed move in x, y movement, and the nozzle move z direction or vice versa. Yeah, the nozzle can move x, y, and this is in z direction. Yeah, okay. But for the light-based 3D printing polymer processing, it used only the z-axis up and down movement. It can be the platform that contain the polymers, pre-polymers is come up and down, or this the how to say this the bed, yeah, the bed, yeah, can come down, up and down. Okay, and the printing time process. This melting base slow to fast, but this process is very fast. Yeah, yeah. But however, it depends on the how the photo initiator edit. Yeah, this to control how fast the curing process of the liquid. It depend also on that. Okay, but in the left side depend on how fast of the solidification process of the melt polymer. Okay, this is the example of those two type of the 3D printing. This is the melting base. Let's see. Yeah, so the platform or the bed move down. In this case, move down. Yeah, and you know the nozzle can move in X, Y directions, but the platform move in Z directions, and we can result this product. But you know, this is the time is faster. Yeah, actual process of this process is not so fast like this. Yeah. Okay, let's see the next process. Yeah, this is liquid base or light base. Yeah, you can see here very fast process. Yeah, see, just drag it drag it up, then suddenly have the final product. Yeah. Okay. Wow, that's very great. It's amazing process of the modern 3D printing. Okay. Yeah, see. It is the real timing process. You can see it's very fast process. So the polymerization occur to form the solid polymer is by light. Yeah, by light.
Interesting.
Okay. They sell the product resin lab resin labs. Yeah. Very fast process. And we can also design the complicated design of the product. Okay. Okay. This is the fourth topic. Yeah. Polymer recycling. Because of the environmental issue, we have to consider this issue in our daily life. Yeah. So we have also to pay attention to the polymer product, to recycle it, to reduce the reuse and reuse of the polymer material, so it can control or unpolluted, yeah, the environmental. Okay, what the needs versus challenge? The needs of the polymer recycle is the stable supply of materials with reliable collections and sorting, economical, proven and environmentally sound recycling process, and used application for the recycled materials. But the challenge, we have can make 10 or 12 main polymer types, yeah, for the recycled polymer, and we should, yeah, think about the thousands blends of the polymers, and we can add the additive and also the impurities in supply, because it has become the problems. Yeah, yeah, it's labels, glass, dirt, etc., and it will affect to the process of the recycle process. This is the types of the polymers as I said previously. And the basic recycle step is sorting, size reduction, densification, pulverization, and melt filtrations. Yeah, for the sorting, it can be manual, very common. Yeah, because sorting by human is easier and cheaper than the by machine. But we can also be sorting by machine with the centrifugal based on fluxing methods. Yeah, by machine. Yeah. And also by optical, yeah, and also this is the expensive method to sorting the materials, yeah, by using spectroscopy, infrared, and automation possible. And this is by using conveyor, yeah, that use the density difference. So this input feeding, and we can divide which one more light. So we can maybe over there and so on, and because of density difference. Follow it by size reduction by using shredder like this. So we crush the polymers, become small parts by using shredder like this, or by using a rotary knife like this. And we also densifications. Yeah, basic purpose of the densification is to reduce the volume. Yeah, and it is about almost from 20 kilograms per meter cubic to almost 400 kilograms per meter cubic, and also polymerizations by heat it up and compact it. And then pulverizations, convert clean plastic waste into powder. And then after this process, some of the product can actually be used if low purity requirement. For example, recycled plastic lumber, for the example. And then melt filtrations. That's improve purity of purified polymer. And we can use the concept of melt filtration by melt it, shove it through the screen. And maybe we can add by chemical processing. Yeah, chemical processing. Yeah, if it is difficult to use mechanical filtration. Okay, then finally we get the polymer pellets, filament, sheets as the raw material for the polymer processing product. Okay, I think it is the final part of our presentation today. It is, let's see a bit technical cases for the polymer processing. It is a bit technical. Yeah. In the case one, we have the PVC, how the relations of the viscosity of the versus processing temperature. We have here, for example, viscosity of an amorphous PVC as measured. It is about 3.9 times 10 rank 5 Pascal second at the temperature of 122 degrees C. Yeah, for the processing, the viscosity should be at this viscosity. At what temperature should the processing be done? So we are design the chamber. No matter it can be extrusions or injection molding. Yeah, the principle is how to control temperature, yeah, of the processing of PVC in order the viscosity can be kept between 500 and 5,000 and 20,000 Pascal second. Yeah. So this by using these equations, as the previously I give you the slide, yeah, we can calculate the temperature of the processing of the PVC. Yeah, after we get this one, yeah, and we get the T, yeah, T from this equation, and input all unit here and the value, and finally we get T about 139 degrees C. Yeah, yeah. If this use the this Yeah, the viscosity, viscosity of the polymer as measured. Yeah, but the problem is how the viscosity, if the viscosity like in the ring like this, what the temperature. This is a T1. You can get that, and with the lowest acceptable viscosity, for example, 5,000, sorry, the temperature will be calculated. We get 149 degrees C. Therefore, the processing of PVC, in this case of the viscosity range, should be done within the temperature range of this T1 and T2. Yeah. So, if we use the temperature out of this range, so the PVC cannot be keep the viscosity in this range. Okay. Okay, let's see the next example. Viscosity versus molecular weight of polyethylene. Yeah. We have zero viscosity of linear polyethylene like this at the temperature 190 degrees C. Yeah. For the zero viscosity as known as the for the comparisons with the molecular weight is the constants like this, and the constant alpha is 3.5, and then the temperature dependence of the viscosity polyethylene in melt can be estimated with Arrhenius type equations. The question is, what is the molecular weight of polyethylene, and how much should the temperature be altered in order to reduce the viscosity by half? Yeah, what the temperature, yeah, should be altered in order to reduce viscosity by half of the viscosity. Okay, let's see. After entering the value to these equations, yeah, and we get the molecular weight 630,000 grams per mole, and then using Arrhenius, we can get the final calculation of temperature. It's like this. Remember, the temperatures is still absolute temperature in Kelvin, so we have to convert to the Celsius temperature. And therefore, in order to reduce the viscosity by half, the temperature should be increased by 51 degrees C. Yeah. From this 160 degrees C to 241. Yeah. Okay. The next example, how to calculate the creep of polypropylene. Yeah. For example, if the polypropylene rod attached to the ceiling with the length is the 200 millimeter, yeah, and the width is 25 millimeters, thickness is 3 millimeters, and then loaded with the 30 kilograms. How much will the polymer creep in 2 minutes when the creep compliance followed by these equations? Yeah, we can calculate this. We have the stress imposed of the cross section of the polymers. It's like this: 3.9 times 10 ranked 6 power 6 Newton per millimeter square. Sorry, and then we can calculate the creep with the obtained strain like this, where the equation followed by this, and then by calculated with the 2 minutes, yeah, we can calculate strain or creep become 0.0031. So during 3 minutes, yeah, the change of length of the polyethylene, yeah, polypropylene, sorry, polypropylene become 200 initial, yeah, with the percents of the ratio of the strain like this. We can get the deformations change is become 0.62 millimeter. So the creep occur on the polypropylene rod is this value. The last case, viscosity versus chain length for polystyrene. Yeah, when the polymer chains are long enough to form stable entanglements longer than critical chain length, and the polymer viscosity eta and chain length ZW can be connected by this equation where K is constant. Yeah, we have the condition like this. The usual processing temperature of polystyrene cup is the temperature like this, 160 degrees C, and melt viscosity is time 1.5 times 2 over 2 rank 2 Pascal second, provided that the main chain length is 800, and the quality of the polymer, however, varies. One day the main chain length become 960. Then the processing is tuned for the particular viscosity range. The equations, how should the processing temperature be altered so that the melt viscosity would be still, yeah, in 1.5 times 10 power 2 Pascal second. The conditions of the glass transition temperature of polystyrene is 100 degrees C. We can calculate it. After enter the equation, we get the zero viscosity become this, and viscosity of the novel polymer grade at the 160 degrees C, yeah, become this. Yeah. Okay. Then by entering the glass transition temperature for the equations, we can get log of the viscosity with the over the viscosity of in glass transition. Yeah, and we get the viscosity in glass transition. This. Then we get the new processing temperature can be solved by using WLF equations. Yeah, this. Then next calculated, we can get T2. The new temperature processing is 163.6 degrees C. Yeah. Okay, therefore, since usual processing temperature of polystyrene cups T1 is 160 degrees C, then to keep the melt viscosity remain same or unchanged during processing, yeah, we would alter the processing temperature T2 at this temperature, 163.6 degrees C, or higher than usual, about 4 degrees C. Okay, I think that's all my presentation to give you introduction of the polymer processing instrument today. Hope you have some additional information for this. Thank you, and please give the questions.
Thank you, Dr. Sigit, for the very insightful and comprehensive and very interesting presentation. Okay, so class, can we have a question from, okay, we have a question in the chat room. So I would like to read the question to you, Dr. Sigit.
Yeah.
Okay, for injection from Dania Adila,
Yeah.
okay, the master student of Faculty of Applied Sciences. Okay, for injection or extrusion molding process, from your experience, is there any possible defect or problem occur during the process, and how can we prevent the problem?
Okay, very nice questions. Yeah. My share already stopped. Yeah.
Yes.
Oh, sorry. I will reshare again.
Okay.
Sorry, I am not used to the Google Meet.
Currently in okay, you can share again.
Okay, this one. RG, yeah.
Okay.
Let's see the injection with this one. Extrusion and injection.
Yes. Is there any defect?
Yeah. Normally, defect can rise from the many things, many source. Yeah, many source.
Yes.
Yeah, it can be caused by the die or the nozzle on the heating process. Many part of the extrusion can rise the problem. Yeah, can affect the product. Yeah, for example, the porous within the final product, because of the this parameter, this parameter. This is a very critical parameter, should be considered during the process of the polymer materials. Yeah, for example, melting point. When the melting point of the polymer is out of the or lower than the process of this, yeah, lower the, I mean the heater's temperature lower than the melting point of the polymers, we will find the many problem, even in very initial stage, yeah, yeah, because of the barrel heat, yeah, heater too low, yeah. So the polymer will difficult to drag, yeah, to flow there, to flow to the nozzle, yeah, maybe stuck here, yeah. But if the heater is too high, yeah, too high, I mean the drag flow is, the viscosity is very low, very low, to so the polymer will very easy to move there, yeah. So when it come to the nozzle, it is too too low viscosity, and you know the dies we will not work properly, yeah, because of the polymer insert enter to the dies, it's too low of the viscosity, yeah,
Yes.
yeah. The we it need maybe more time to wait, yeah, before it released, yeah,
Yes. So we
release.
have to take note on the parameter that melting point, the viscosity, modulus elasticity, and the curing, and the things that needs to be take as a precaution lah, in order to do this processing. Okay, so the next question is from Muhammad Shauki. So he asked for the price of the 3D printer. Is it expensive?
Wow, that's good.
Because I think it is interesting, right?
Yeah.
Interesting process. The 3D printer.
Okay, thank you very much. Who the questions from?
Muhammad Shauki.
Muhammad Shauki.
Yeah.
Okay, I think in the near future we will buy the cheapest one. Yeah. Today we have the models type of 3D printing in many various type, from the cheapest one to the expensive one. Yeah, the expensive one.
Yes.
We can buy the cheapest one from in marketplace, many marketplace or online. Yeah, maybe the range it is about. I'm not really know the convert to ringgit. How many rupiah one ringgit? Maybe 300 on 4,000 for 3,000 or 400.
I'm not sure. I think 400 is equal to
4,000.
1 million. 400 equal to 1 million, 1 juta, 1 million rupiah.
Oh, I see. So,
Ah.
okay, 1 ringgit equal to 4,000 rupiah.
Yeah.
So the price of the cheapest model of the 3D printing, it is about 400 times 7. Yeah, to 2,000. 2,000 something up to 3,000 ringgit.
There are many range of price for this printer, right?
But
it's based
from
on what?
For the more expensive one, you can buy. It is about 50 million rupiah. Yeah, it is maybe about 10,000 to 10,000 ringgit.
Ringgit Malaysia. So Shauki, there are many range of price for this 3D printer, if you like. Okay, and we have another question from our PhD student, Faiz Aizamdin. Okay, he said that in the 3D printing process, I can distinguish that 3D printing process is usually used for the production of smaller product or parts compared to other polymer processes. What is your comment on the cost and the production rate in 3D printing process? Is it reliable over the capacity of making complex parts?
The advantages of the 3D printing process, is we can make the very accurate design, very complicated design. As long as we can design it by AutoCAD or some 3D modeling, computer aid, we can make it by 3D printing. We can adjust it, how precision it depend on how we can adjust the parameters of the 3D printing process. What we are talking about is 3D printing of polymer. In the other side, the 3D printing not also can produce the prototype from polymer, but also from with metal materials also. But the comparison of the price of the 3D printing of polymer with the metal is with the earth and sky.
It's a very big difference, right?
The price. For example, for polymer, the expensive one, it is about 50 million rupiah. For the metal, it's around, it may be reached 20 billion, trillion. Milliar rupiah.
Oh. Million rupiah equal to
1,000 times.
1,000 times of. Okay, so very expensive for the metal.
Very expensive. For metal.
But this 3D printing can be used also for metal. Metal-based material, right? Okay. How about the capacity of making the capacity of this 3D printing? The production rate.
Okay. If we use the melting paste, it can, one product depend on the size. For example, our size, like the mouse, this you can see this one. Like the mouse. Maybe we need about 2 hours. 2 hours. 2 hours to 10 hours, depend on how we design the the density of the product. More higher the density, more precision, the more accurate the size. More slow the time to produce.
Okay, so compared to injection and extrusion, this one is a bit lower in the production rate compared to the injection and extrusion, right?
But we can make it the more the advantages is the precision
and the complicated.
But we can also make the fastest one by using the light-based 3D printing, as I show the movie. It is very fast. Yeah, just put the bed on the top and pull it out, and suddenly the product produced. Yeah, it's very fast.
Yes,
In
very
second.
fast.
In second, yeah.
Okay. Okay, Faiz, is that answer your question? Okay, now we go to the next question from Shazwani Malik, also our postgrad students. Okay, Assalamualaikum, Dr. Sigit. I have two questions here. Okay, first, do a bio-based polymer differs to biopolymer? Do a bio-based polymer differs to biopolymer? And the second one is, what is the difference between bio-based polymer and biodegradable polymers? Okay, and are there any differences between those polymers? If do, how or what are the main key to differentiate those terms in polymer?
Okay.
Okay.
Okay. I answer the second question first.
Okay.
Biodegradable, it is different with biodegradable, biodegradable and
Polymer.
polymer. Yeah.
Yes.
Biodegradable means the polymers can be degraded by
biological process.
Yes, by process.
Yeah.
Like the bacteria and so on. Yeah. But biopolymers mean it is the polymer can be adaptation, yeah, mixed within our body. Yeah.
Natural resources.
Yeah, natural resources. Yeah.
Yes.
Okay,
that is the difference.
Yeah, that's different. For the first questions, I cannot hear clearly because some internet. Yeah.
What do a bio-based polymer differs from biopolymer? I think you have answered the question.
Yeah, yeah.
The difference between bio-based polymer and biopolymer.
Okay. So, I see. Yeah. Bio-based polymer and biopolymer. Yeah, I think the difference is about the resource. Yeah. Bio-based polymer and biopolymer. I think some terms it is the same. Yeah, biopolymer and bio-based.
Yeah, I think this is the same.
Yeah, it's the same. Yeah. Maybe bio-based mean maybe the base of materials is if you combine with another non-bio, maybe the bio-based is more than 50%. So we can is bio-based.
Call it bio-based polymer, like green polymer, like something like
polymer.
that.
Yeah.
Okay. It's based on the composition. It reached 50% over, so we call it green polymer.
Yeah, like that.
So we have 3 more questions. Is it okay, Dr. Sigit?
It is okay. It's okay. We have more.
Okay, from Muhammad Al Hadi. Okay, in multiple thin film processing, which involve deposition of polymeric membranes along with other material, which is metal oxide. If the polymer used has low melting temperature but was used as the bottom layer, is there still a way to anneal the film at high temperature?
Wow. Well, I think it is very specific cases.
Yeah.
Very specific cases to produce one. I didn't know in detail. I didn't know in detail. I have no experience about this.
It's a combination between polymer and metal, I think.
Yeah.
Blending.
Yeah, maybe we need to know the detail of the case.
Yeah.
So maybe it cannot be answered in the short way.
Because it's involved 2 material which are very different melting temperature.
Okay.
So it's on the blending things. That is the thing that we need to consider, right?
Okay, I see. The point is like that. Yeah. We have to close. We have to make the melting point closer. Yeah.
Yes.
If the range of 2 kind of polymer, the temperature melting temperature is too high, the difference is maybe cannot be blended well.
Yes.
Yeah.
That is the problem that we will face if the difference of the melting point is too broad.
Yeah.
Yeah. So we have another question from Nazrin Roslan, also from also our master student, which is the thermoforming process seems quite simple and easy. From your point of view, what are the main challenge in thermoforming process?
Yeah. I think thermal forming process is the most easy because we just deform the polymer. Yeah, you know, it is almost similar with the metal forming.
Yes.
Because as we know, with metal is very easy to form. Yeah, it has a wide range of plastic deformations. Yeah, area, so we can make easily of the metals by forming. Yeah, even in the cold forming. But the polymer, because of the characteristic of tensile, yeah, the polymer very difficult to form with in the plastic. Yeah, of course, metal also. We have to form in the plastic area. Yeah, plastic area. Of course, it need heating. Yeah, it need heating. Because to get the plastic area of the polymer, it need to heat up the polymer to enter the plastic area. After that, we just deform it to a specific form. Yeah, so we can get. After that, we cool it to keep this polymer in the deformed conditions. Yeah, for example, if we make a curve like this of the polymer, we heat up the polymer and compress this, and we can after cooled we can release the compressions and the mold. We can get the final product of the heat compressed polymer. Yeah.
Okay. So what is the difference between thermoforming and compression molding? Is there a difference, right?
Yeah, the thermoforming in some case, in some case similar with the molding, compression molding, compression molding. But in the compression, maybe in a compression molding, the heat is maybe lower than the thermoforming. Yeah.
Yes. Okay, Dr. Sigit, we have another question from Nur Fatiha on 3D printing again. Okay, so very interesting topic on 3D printing.
Yeah.
So what elements in the light that help in the polymerization process of the 3D printing?
Pardon, Doctor?
What elements in the light?
What kind of light?
What elements in the light that help in the polymerization? Light.
What
cahaya,
kind of
cahaya.
Yeah. Panjang gelombang maksudnya.
Yeah. That helps in the polymerization.
Okay. Actually, the polymerization can be initiated by light. Yeah, by light. So the light is can be specific in several meter of the lambda panjang wavelength. Yeah. Sometimes the photo initiator can work in the wide range. Yeah, advanced. It depends on the type of photo initiator. Yeah. For example, I ever been used the titanium based photo initiator in acrylic monomers. Yeah. And I use the projector light using the projector slide. It can work. I mean the range of wavelength, it is about 300 to 700. Yeah, a bit shift to the UV. Yeah, UV until the visible light.
Okay, it based on the wavelength of the lights, right?
Yeah, based on the light, and based on the specific of photo initiator.
Yes,
There are many type of photo initiator and many with wavelength can be used, yeah, to initiate the process.
Okay. Is it help you, Nur Fatiha, with the answer from Dr. Sigit? So we have another one from Nur Shika Rabia. Yeah. What kind of product usually can be formed from the 3D printing?
Wow, this many product. Many product. Yeah. If you buy the cheapest one of 3D printing of the melt-based 3D printer, yeah, you can use, for example, the materials as the feeder material. We call this filament, like polypropylene, polyethylene, polystyrene, and then many thermoplastic can be used right now, and it is the price already reduced for the initial release. Yeah, initially it is a bit expensive, but now we can find it cheaper, maybe a half than compared to the previous one.
Okay, so is it only for thermoplastic material? Currently?
Yeah, currently mostly thermoplastic, but also developed in the thermoset. Yeah, but already developed with the thermoset. Yeah, yeah. For example, you know, the polyurethane. Yeah.
Yes, polyurethane.
Yeah.
Okay, so class, you can open up your microphone and raise up your question directly to Dr. Sigit if you want. Okay, we have another one. Okay, Aliatul Nashra.
Do injection and extrusion can use the same machine for part like screw, because the difference is at the mold and die, right?
Pardon, the injection?
The injection and extrusion machine are the same for the screw part.
Yeah, we can use this. We can injection molding with the extrusion. Yeah, in the all machine design of the injection, usually they have the extrusion part, the machine. Yeah.
So is there any? Okay, is there any difference of screw between injection and extrusion?
Oh, yeah, I think it is similar. Yeah, similar. Basically, the extrusion is the part of the injection. Yeah, the part machine of injection. You can continue make with the injection molding after we design the extrusion machine.
Yes. Okay. Does it help you, Aliatu?
Yes.
Okay. One more question from Nurul Ain Najiha. My question is, what is your comment on the emergence of 3D printing technique compared to the conventional methods, as 3D printing has attracted huge interest nowadays, which leads to the idea of 4D printing?
Wow. 4D printing, yeah. Maybe I have no idea what about the 4D. You mean the? Yeah.
The question is, what is your comment on the 3D printing compared to the conventional methods? And because this kind of method is very attractive and currently leads to the product to the innovation of the new printing methods, which is 4D printing.
Yeah, basically in the polymer processing for thermoplastic, the very basic principle is how we make the product from the melting of polymer. Yeah, for the melting. Yeah, it is for thermoplastic. Yeah, for thermoplastic polymer, we have to melt it first and then cast or mold with the molding or casting part to have the product, to get the product. How it different with the conventional one, with the modern one like 3D printing? It is related to just the method. Yeah, the conventional one use the complicated method and mass production. Yeah, we cannot order only one piece of product by using the extrusion, injection molding, only one. For example, we buy only one plastic packaging on to the company. It is impossible. We have to buy several tons, right?
Yes.
Yeah,
Yes.
but by using the 3D printing, we can print out only one product. Yeah, for example, we only we print one cup of the water content, yeah, water container. Yeah, we can print only one by 3D printing. We can order only one, yeah, to the company.
Yes.
Yeah, the design depend on us. Yeah, depend ourselves. We send the design. Please print this, gitu, like that.
Yes. If you want for conventional methods is you can produce a product in a bulk, right? But for printing process, you can produce a product like 1, 2, or 3. That is the advantages of 3D printing, I think. So, any more question from students? MSc 513 students?
Internet connection a bit, yeah.
A bit slow.
Yeah.
So
maybe if we combine the method of 3D printing with the the era of 4.0, already some people and some company has already do this. Yeah, so they just remote if someone order the product, for example, I am the production of the product, just ask me, I print by using the mobile phone, and my machine in my home or in my industry print it up.
Yeah. You just the technology, right?
Yeah.
Okay, that is the beauty of 3D and 4D printing in the future, I think. So, do we have another one question? Maybe the last one, which is from Muhammad Al Hadi. Okay. In Sol-Gel electrospinning process, polymer was added to help the process of producing nanofibers by providing the needed viscosity to the solution. It is on the electrospinning process, Dr. Sigit.
Yeah.
Okay. However, when annealing process was performed to get rid, the nanofiber structure is also affected. Is that a simple way to solve it?
Okay, again, it is a very specific case to the processing of polymers, polymers fiber, to make a fiber by using electrospinning.
Nanofibers, yes, nanofibers using electrospinning.
Electrospinning. We can, maybe we can find the calculation method of how the effect of the viscosity on the formations of the agglomerations. I mean, because the polymerization process is very affected by the how the monomer, it can be polymerized related to the process of electrospinning.
Okay, is it help you, Muhammad Al Hadi?
Actually, in my nanofiber fabrication, I'm just adding the polymer into this metal oxide solder to help increase the viscosity so that the nanofiber will be produced. But after that, I just want the metal oxide to remain and polymer to be rid of, to be what we call to be get rid lah.
So,
But however, due to the annealing process itself, the nanofiber breaks because maybe there's some polymer in the metal oxide network.
Because of the mixing
Because
before that.
mixing, yes. Mixing is not there.
So, Dr. Sigit, can you comment on this?
Thank you.
Okay. So the polymer in this case become the agent or template for template to make a nanofiber of metal oxide.
Yes, I think so.
How the so your problem is when it annealing the nanofiber of metal oxide, when it's annealing,
the fiber will
it break.
Yes.
I still have no idea about this. maybe some it is the nanofiber got like thermal shock. Thermal shock. Maybe the strategy is to the annealing process is to with the step annealing. For example, if you annealing it in several hundred, please in the first initial annealing process you take the, for example, 100 degrees C and hold it several times and increase again, hold and several times until you get the final annealing temperature you want. Maybe that will help.
I think it's because of the mixing process. I think the annealing process or something that is that leads to this kind of problem. Okay. So is there any more question? I think there's no more question in the chat room. And also any more question, class? Okay. No more question, I think, Dr. Sigit. So that's the end of our session today, Dr. Sigit. So that is a very interesting sharing session, and I hope this will benefit my students. Okay, Faculty of Applied Sciences student. We have students, undergraduate student and also postgraduate student of Faculty of Applied Sciences. And before we end our session, okay, on behalf of Faculty of Applied Sciences, I would like to congratulate and say our gratitude to Dr. Sigit, okay, for your insightful and very interesting talk today. And not forget to everyone who participate this guest lecture series session. Thank you very much. And Dr. Sigit, I hope we can work together again in the future. And we will have a lecture series together again.
Hope so.
So thank you too to Miss Amelia Rashida for arrange this kind of lecture series. It's a great program. Okay, thank you, Dr. Amelia.
You're most welcome, Doctor.
Okay, so is there anything you want to talk to say to the audience, Dr. Sigit?
Okay. For the students, I'm sorry because my lecture today is not accommodate the nano polymer. I only focus on the processing of the pure polymer, because in my opinion, when we are going to talk about nanomaterials related to the polymer, normally we use the polymer as the composite with other materials. For example, in the case of Muhammad Al-Hadi, it used to binder, like a binder to make a nano oxide, metal oxide.
Yes.
Like that. Okay. So by the way, nice to meet you all in this session.
Nice to meet you too, Dr. Sigit. And thank you to the participant from ITS. I think we have some student from ITS, right? So who joined this session. So thank you so much. So till then, thank you so much to all and see you again, Dr. Sigit.
See you.
Okay, see you.
Thank you. Assalamualaikum.
Waalaikumsalam. Thank you.
Thank you, Doctor.
Thank you.
Waalaikumsalam. Thank you, Doctor.
Welcome all.
Okay.
Thank you, Doctor.
Thank you so much.